on history, laws, and mass spec, you could figure out some of this together. All right, so number 44 was the one with the Zorgs. And whose experiment kind of was this supposed to be resembling? Whenever you had like a set number of masses, we had 4 different masses, and it was basically trying to figure out like the quantity that went into each of those. Yeah. Yeah, Millikan's oil drop experiment was what this was kind of mimicking. Now, I give you Zorg, so I can give you any unit, I give you puppy dogs and unicorns, but if you can figure out how many parts from the whole, that's going to be basically what Millikan did with the oil drop experiment. So this was, I call it lowest common denominator. Greatest common factor is another phrase for that mathematically. So you should have been able to take the Zorg's charge be, I'm going to have to pull the data. You guys wrote down your data, I did not. But all you're going to basically do is take how many times the Zorg's charge goes into each of those masses given. This is page 79. And not page 79, this is page. All right, so you have like 4.8 times 10 to the negative 9th, 9.6 times 10 to the negative 9th, and so forth. So using that, when you look for the greatest common factor, that it should have been this 1.6 times 10 to the negative 9th. It's the only number that went into each of those with an even integer, because you can't have like half or a third of an electron. So for each of those, this actually does represent the charge of an electron in Zorgs, is how it's phrased. In A, it went in 3 times, B, it went in 6 times, C, it went in 4 times, and D, it went in 8 times. So you're simply dividing the number they gave you with this number right here, which I found to be the least common, or greatest common factor. Yeah.
So the negative 1.6, that's just like given.
It's not given here.
It's just like
this one is resembling what they gave you in the book for the question regarding mass of an electron, which was like 9.5. Somebody wrote this down for me. Wasn't that, or the charge of an electron? Times 10 to like the negative 31st. So it's resembling that experiment that Millikan did, where he took the charge of the electron and divided it into the charges of the oil drops that he had from his experiment. This number was not given. I basically whittled down from the data given in this data table here what the greatest common multiple would be to achieve those values. So it's kind of a guessing check. Figure out what goes into each of this with a whole integer. So we took like 40. If you look for like a common multiple between, you guys have your data probably written down. 4.8, 9.6, 6.4. 4.8, 9.6, 6.4, and 12.8. And these are all times 10 to the negative 9. What number goes into all of those? Okay, some people are saying 12 or 1.2. I think it didn't go into one of them. Which one? 60, no, it doesn't go into that. 1.2 didn't go into one of these, but 1.6 will go into each of these an even number of times. And so that's basically you just looking at the data and looking for a common factor that would go into each of those full integer. So that one goes into 4.8 3 times, and then sequentially 6 times, 4 times, and 8 times. So that's just a looking at data question, and then going back to your experiments that you guys learned about in your video. Yeah.
How did you know what to do in the question that was what you're supposed to do?
So if it told you the total charge of the drop, and it says what is the charge of the electron? So based on the results here, what is the charge of the electron in Zorgs? Because it told you the total charge in Zorgs. You know that you can't have partial electrons. You have a certain number of them. I read it as, here's the total, how many parts are in the total? So here's the total charge, how many parts go in to make that total charge? So that's why it said to look for the number of electrons. We'll practice some more with that. Please don't be too concerned right now. Yeah. That's going to be something we'll actually utilize it in the next semester. We'll use we'll have to talk about some atomic structure now, and we'll talk a whole lot of atomic structure then. That's to determine the total charge of an electron if you know its mass, or vice versa. Determine mass of a set of electrons if you know its charge. Okay, so it would be like a one single step stoichiometry problem. Okay, but we are going to talk about that one when I think of 45. Okay, so 45 you guys had microcoulombs, and I only wanted you to do this one so you could understand how to use micro, the measurement micro, which was the from King Henry died by drinking chocolate milk, ... What comes next? ... Micro, ... Nano, ... Pico, okay? So that's a relationship between like kilograms and grams, or micrograms and grams. And so understanding how to use this number line, which was in your math video from day one if you needed an update on math, was for a base unit for a year. I can have one, is this in grams or coulomb? 1 coulomb, which is a base unit, would be equal to 1, 0, 0, 0, these decimals count as zeros, and then 0, that's 10 to the 6 microcoulombs. So that is the relationship between the two. Okay, say again? What do you say? No, you have 1,000,000 microcoulombs in a coulomb. So you have one big unit with a ton of little units. Some people will put a negative exponent on there, but I don't find that really friendly to, logical sense. All right, so looking back at that question, how many excess electrons were required to basically collect that entire charge and then sequentially the mass? So, if I can show you the stoichiometry first, you had your microcoulombs. This is the relationship between coulomb and microcoulomb because of the metric system prefixes. This was a number given to you in terms of the charge of the individual electron that was in the textbook, and I think it was in the textbook. It wasn't given to you in that question. So you had to go back to look at the charge. I think you asked me about coulombs yesterday. We'll talk about Coulomb's law later, but this is just us using the unit of coulombs. So utilizing that as the charge of one electron, you can cancel out everything except for the number of electrons, and you get the excess electrons, which built up that charge they stated as 9.36 times 10 to the 13th electrons. Who got that? Okay, I did see that mostly on some of your papers. Good. So if that's the extra electrons, and this was given as the as the mass of the electrons in kilograms. This was in the textbook a couple of pages before. I wrote it as why I wrote it like that. I think that's actually how it said in the textbook, but it's 9 times 10 to the negative 31st, like you said, Emily, too, and that's kilograms per 1 electron. So taking your number of electrons, canceling it out, you get to kilograms, and then from there, you should get 8.5 times 10 to the negative 17th kilograms, which is the total mass of all of those electrons. It's a lot of electrons. Like a ton of electrons, but see how the mass is so minor, right, to the negative 17th. So what do we normally assume about the mass of an electron? Zero. It's zero. It's negligible. And this is kind of the thought process behind why we do that. Yes?
So you didn't say you got the 9.36, but you didn't do it that way. So I don't know.
I'll look at your math. We're running out of time. We got to go talk about mass spec, okay? So this is a process. If you problem solve another way, I'm just reinforcing stoichiometry basically the entire year. Okay, I will never solve anything basically via proportion except for like a gas law. All right, and then 120, again, via stoichiometry, had the lead atoms. I don't want to read the whole thing to you, but it was lead air pollution, 1.5 micrograms per meter cubed, and assuming the total lung capacity was 5.5, you had to go ahead and determine how many would be in the air. So this was a constant or a conversion factor given to you, and your job was to figure out how many lead atoms were present. I have to scroll up, unfortunately, so here we go. So your lung capacity is 5.5. That's your given starting point. This is your conversion factor. You can't quite use it just yet. You actually have to figure out the relationship between liters and meters cubed, which takes us just a little bit of time. So liter to milliliter is quite easy. This 1 centimeter cubed to 1 milliliter can basically use for anything to convert from a volume in a liter form to a volume in a cubic length form. And so that's going to be your probably point where you did not realize that's a true fact. That's true for basically everything. So whenever you're now going to meters cubed, because that's our conversion factors units, whenever you cube a metric relationship unit, you also cube the number as well. So that's meters cubed, 1 cubed, cubic centimeters, and that 100 is also cubed, and that's going to be where some people made a mistake. That's a mistake that Honors Chem, and they have a test next week. This is the mistake they will make, I guarantee you. They have a test kind of on this. And then meters cubed will cancel when I utilize the conversion factor of 1.5 grams of lead atoms. And then getting me from grams to, micrograms to grams. This is the metric system again, 10 to the 6 micrograms in 1 gram. And then finally, we could use actual chemistry and get from grams of lead using the molar mass to moles of lead, and then from moles of lead using Avogadro's number to atoms of lead. Like a 15-step process, but all of these right here were old school. This stuff right here is old school. Everything's old school. It's just putting a lot of that together, which was probably more difficult. So you should have approximately 2.4 times 10 to the 13th atoms. We got something like that. All right. Any like big general questions about this? No? Yay? Smile or something, guys. You're just looking so somber. Okay. Like I said, I'm videoing and I'll put the answer key up for this. All right, so I'm gonna adjust. I'm just gonna do our notes right now first, and then give you two example problems. The two example problems will be two things I would definitely write down. It's a super easy process, but I want to review atomic mass first before I go into mass spectrometry. So you saw mass spec stuff on the end of the video, right? Those of you, what I do is I give you your videos and you need to watch them. If you don't watch them, you get lost in class and then you feel like crap. You feel frustrated. You don't feel like you know what's going on. So I was going to put them on Edpuzzle. Do you guys know what that is?
Yes.
Where it forces you to watch the video and I will not let you speed it up. I was going to do that, but I try to value your time. You guys, some of you guys can listen to me at Mickey Mouse speed and be just fine. Some of you guys need to slow me down. So you guys need to rewatch it. So Edpuzzle has a little more restrictions on it, and that's why I'm doing that with Honors Chem this year, not with AP Chem, but I need you guys to watch your videos. So this is a quick review of isotopes. Isotopes you've dealt with for a while. Basically, we say, oh, an atom with a different mass or a different number of neutrons is an isotope. But that's not 100% true. Literally every atom in the entire universe is an isotope. Every single one of them. Okay? But they're all an isotope of a given element. And that given element can sometimes have 2 isotopes, 3 isotopes, or 16 isotopes. These are all just things that are occurring naturally in nature. So isotopes of a given element is how I'll phrase that, to say isotopes of an element have the same number of protons but a different number of neutrons. That different number of neutrons gives it a what? A different mass, right? Sorry, I don't know what that noise is. You guys hear this too? Is that band? Is that the movie?
Yeah.
Next door to us? I'm gonna go shut somebody's class down. All right, so neutrons are different, which would then give us a different mass overall. Because what makes up the mass of an atom? Right, neutrons plus protons. That's going to give us the mass of an atom. Okay, whenever we're talking about A and Z numbers, it's sometimes counterintuitive because you want to go, oh, A is atomic number. No, it's actually different. Z number, whenever it's phrased that way, the Z number is the atomic number, and that's actually because of something called the ZEF. Can you remember ZEF from? Thank you. So ZEF is effective nuclear charge, and so Z means nucleus. But what's in the nucleus? Protons and neutrons, but protons is like the key player because it's the identity of the element. So the Z number is just a play off something called ZEF, or nuclear effective charge. The A number is the total mass. That's for that individual isotope, which can differ between different isotopes of the same element. And I just wanted to show you guys this. This is in your textbook in chapter 2. If you ever need to reference something like that, it's here. With respect to the masses that we've been speaking of, yes, an electron does have a mass, but we generally regard it as negligible in the grand scheme of things because it's significantly lower than the proton and neutron mass, which is why we only include protons and neutrons in the mass of the overall atom. Okay, so this is the A to Z notation. This is how you'll always see it, but we're actually going to write one like it now, okay? So let's do magnesium. Magnesium with a mass of 25. Okay, how would you write that? Mg is our letter, our symbol. Where would the mass go? Upper corner, okay. So the mass of that magnesium isotope is 25, and then what number goes down here? Why 12?
Because the number of protons.
Right, it's the number of protons. It's also the atomic number. It's the number on the periodic table. So this is just an atom of magnesium, and that's the A to Z notation. Another way to write that is magnesium dash 25. And that's the mass notation. Mass notation versus the A to C notation. And that's simply because I don't have to give you the Z number. You will always have the periodic table in front of you. You can always find that if you need it, okay? But the mass will change because different isotopes of that individual atom can exist. So I have to tell you the mass if I'm trying to get you some specific information, because what does it say on the periodic table for magnesium? 24.30. Is there an atom of magnesium that weighs that? Yeah, 50-50 here. No, there's literally not a single atom that weighs 24.30, because that's the average of all the isotopes of magnesium in the world. So I'm going to talk about how to average that mass now. So there's never a single atom that doesn't have a full mass, kind of like this, a full integer, or a whole integer. However, when you start to see some more specific data, they will give you some decimals of that, simply because they do include the masses of the electrons just a teeny bit. All right, so purpose of mass spectrometry, before I go into the average stuff, the purpose of mass spectrometry, this is the end of your video. Turn and talk for a second, tell me what the purpose is.
Yeah, use like heavier things going on. What?
I need to do an average one if I don't have that right here. All right, pause this conversations. Anybody want to tell me what the purpose of mass spectrometry is? Say again? Well, that's our end game, right? To find the average atomic mass. But just the purpose of that makes something to do that. Yeah. What about the isotopes? Like who they are? Like which ones exist? Okay. So mass spectrometry can, one, tell us which isotopes exist of that individual element, because sometimes there's 5 isotopes of oxygen, other ones there's 2 isotopes of chlorine, there's 3 isotopes of hydrogen, there's a lot of different number of isotopes of different elements. Okay, so it can tell us the number of isotopes and something else. Anybody? Say again? How much of it is compared to the other one. So we call that relative abundance. And there it is. Relative abundance. So we want to know the relative abundance of an isotope in a given sample, and we try to sample like the whole world at the same time, but it's hard. So the relative abundance is also called percent of sample, maybe? That's a good way to say it. Okay, so what you guys have done before with average atomic masses is you've been given, like, for example, chlorine 35 and chlorine 37. Those are 2 isotopes of chlorine. And I would tell you, all right, guys, we have 25% chlorine 37 of a sample, and then the rest of it, 75% of it, is chlorine 35. And just like your GPA is weighted, right? Some grade or some classes are more weighted than the others, or more heavily weighted into your overall average. Atomic mass works the same way. So what we would do, and I'm going to do a really simple example first, is we would take our mass times our relative abundance separately, mass times relative abundance, and then we would add them together, and this would be our average. What normally do you guys do in math class for an average at the end? Right, divide by how many numbers you add together. Don't do that, because we have accounted for that when we do our percentages, and we have to recognize the percentages because some things weigh more into the average than others. Obviously, the 35 one does because it's 75%, and what's the molar mass that's chlorine on the periodic table? 35.45. So the number on the periodic table is skewed closer to the one that you have more of. So the one that you have more of is more weighted into your average. So how does this math work out? We're going to take, I'm going to give myself some space here. This was 75% and this was 25%. We're going to take 35 as just our mass, atomic mass units, and we're going to multiply it by the percentage in a decimal form, which is 0.75. Okay, and then we're going to get that equivalence, or what is that product? Say again? 26.25. Is there another number for me? Is that it? Okay. So I've given you 35 as its mass. Let's call it like 34.9967853 something like that. Okay. So 37 is our second one, 37 AMU times 0.25. Oops. And what's that? Say it louder.
9.25.
9.25. Okay. AMU. Okay. So we multiply. And then we'll add. Let's add it together. 35 what? 35.5 AMU. Now, of course, I made up those percentages, but that was pretty close because what's the actual molar mass of chlorine? 35.45. Okay. So when you're doing average masses, you will always be given the mass. You'll always be given the percent or the relative abundance. Multiply them together. Add. That's it. Don't do anything at the end. So the purpose of the mass spec, though, is for us to look at data to get our percentages. So basically now, I want you to look at a graph and get these percentages. So that's the only extra step that's different from Honors Chem to AP Chem. Okay. So you have this grand looking contraption where you have the sample flowing through, and this was explained on the video. The ions or the particulate the particles will come through and be deflected by a magnet. The big fat things don't deflect very much. The little tiny or lightweight things will deflect a lot. When they come to the detector is starting to record their relative abundances by saying, okay, this one hit 100 times, this one hit 50 times, and then we're going to determine the percentage from that. So if this is the deflection pattern, who's deflecting to the back here versus to the front up here? So okay, so I heard heavy things up here and then light things will go up here, just for the deflection pattern. So what we'll get from a reading of this detector is a graph like this. This is in your textbook. I can't remember which chapter, but look for mass spectrometry if you want to see this as well. So I'm using chlorine again as my example. The way the graph is written is the masses of each of the isotopes that are detected will be on the x-axis, and the intensity, also known as relative, actually, I'm just going to put abundance, will be recorded on the y-axis. But it doesn't really quantify the actual percent abundance or the relative abundance. The way it works is the one that gets the most hits, it gets to 100%. And then it does a relative comparison to 100% for the others. So it says I have, out of my whole sample, 100% chlorine 35, and like, guesstimate this for me. Say again? About 30. Okay, we'll go with 30. 30% for chlorine 37. So you will have to guesstimate on these because they won't give you very many graduations on the side. So we have to normalize this data, which just means take percent abundance divided by total percentage of all isotopes times 100, and this will be our true relative abundance percentage. So how does that look here? I'm going to take my percent. Actually, I have some next slide, so I'm actually going to wait here a second. I think I have some next slide. So we're going to take our individual atoms, 35 and 37. Give me a thumbs up and I can move on. Okay. We're going to take our individuals, and this is an example you'll want to write down, okay? Ooh, hold on. I'll go right back to that. I want to go to my example. Here it is, okay. So, using this graphical data, step one, we're normalizing the data, right? So we'll take the intensity or the percent abundance and divide by the total percentage to get the relative abundance. Like I said, you will have to guesstimate from the graph a little bit. My guesstimate might be a little different than yours because I've already solved this for you guys, okay? So we're going to take our chlorine 35, which from the graph it reads 100. So we'll put 100. And then total percentages that are read from the graph, oh, I did use 30, okay. So 100 is coming from the chlorine 35 and the 30% is coming from the chlorine 37. So what we're doing is we're normalizing the percentages for the true percentage. So that's 30, or that division gives us 76.924%. So I'm trying to give us a little bit more specific information here. So I guesstimated 75 over there, but it's 76, so almost 77% chlorine 35. Same exact step, but for chlorine 37. Chlorine 37's true relative abundance or true percentage is it's 30 divided by the total percentages listed here from those isotopes, which is still 130 is our total. Yes, ma'am. Yeah. Sometimes I run out of space on my slides, but that's how you get your percentage, okay? So now, what you should always imagine is if it's a percent, what should all the percentages add up to be? 100. What do these add up to be? 100, okay? So that's why the graph, it's giving us different data because it doesn't assume that we're adding up our percentages to 100, just reading from a detector. We have to normalize it so our percentages are truly representative of their relative abundances, and then assume that, you know, it's a total sample, so it's going to equal 100. So, same thing applies. One second, Megan. Once I get my percentages, how do I find the average atomic mass of chlorine? What did I do over here? Multiply the relative abundance by the, we'll multiply the percentage, which is the relative abundance, by the atomic weight of that individual isotope. Do that for each of the isotopes you have, and then what? Add them up, and then we're done, okay? So, I took my atomic mass 35 times its percent, atomic mass 37 times its percent, add them up 35.46. This one was a little bit better. Question?
Why do they make it to the graph as like fine?
Always 100.
Weird percent.
Is it because a detector is just giving is trying to quantify the greatest hits it gets to be 100, and everything else is maybe percentage of that. That's how the detector gives out data. They probably have some sort of code that will take that and normalize it for them, because scientists are not going to do this themselves, let's be honest, unless you're just reading from a detector.
So it's not like just percent. It's just
No, it's just how the detector reads off data. Yep. Okay, so who feels okay with looking at the graph and finding normalization? Okay, we might need to do one more, okay? So the background of this, sometimes we have to give you a little bit more background about why these things are occurring, so I'm going to go back to those two slides I just skipped for a moment, after you guys give me the thumbs up. Okay, so the reason that we're talking about this now is because it fits in with the historical model, Dalton's model, which in the video you guys saw that he had this atomic model, atomic theory, and there were two things that were actually incorrect. The fact that he said all atoms of that element were the exact same is an incorrect fact now. He thought that because he didn't have the technology. We have the technology to recognize there's different isotopes of a given element. So that's playing off the atomic theory to give us more information about current technology, and then also how we can utilize that to determine more specific information about elements. The graphs that come out can look like this. It's pretty messy. So I would never give anything that messy, but do expect we will have more than two isotopes on some of these. And it's a way to give you the atomic fingerprint of what is actually true about that atom. We'll never see the true average here because these don't give us discrepancies between the integers of, you know, if we're this one right here, you know, 7,550, and then sequentially it goes integers wise. We'll never have an average, which we have to grab ourselves, but we have to pull the data off of these atomic fingerprints. Okay, so that's just some background information. We did this for elements, but there's many compounds out there that are intricate. They have atoms inside of the compounds, right? And can't the atoms inside the compounds be different isotopes? Right? So we have stuff called heavy water. For example, water H2O, and this oxygen here weighs 16 grams. Let me do this one first. Water with an isotope of oxygen that weighs 16 versus water that has an isotope of oxygen that weighs 18. Well, this water total is going to weigh 18.01. That's our normal water right there. This is called heavy water because the oxygen can be heavy, or the hydrogen itself can be heavy actually. But the 18 is just because that oxygen atom has 2 extra neutrons, so that weighs 20. So they can do this with compounds as well, just because the compounds themselves are made up of atoms, which can be of different isotopes. So this next slide has an idea of what this looks like. This is a cocaine bust. Okay, so we have this mass spec down here with different isotopes inside of that molecule, and they could then derive where that gas possibly came from based on historical data. And so they call those atomic fingerprints, or just fingerprints in general, to represent the compounds that are specific to a location based on the isotopes that are at that location. And so we can actually do that with stuff from space. There's different isotopes in compounds found on Mars versus the atmosphere out, in our inner space. So right now, is inner space right outside of
Near space.
near space? Thank you. Inner space, near space. Okay. So we can do it for compounds as well, but I won't ask for too complex that. We're going to stick with elements. And this is just another diagram to show you that they can fragment larger compounds into smaller pieces and then still do the mass spec for the same formulas that they're broken into. And so the same applies. Take your mass times your percent abundance and then get your average. So I already did that. I already did a percent one, so I'm not going to do that right now. And I already did that for water. Here's one more. No, we'll skip down for now. Okay. Do me a favor. Go to the packet. It's going to be 4th page back. 4th page back. I'm going to show you those 2 things that you're going to work on for maybe just 15 minutes. And then open the textbook that you guys, somebody brought to your table. I do have 2 more in here by the luck of somebody sending me some textbooks finally. So 2 extra textbooks if you guys for that. And then turn to page 79. In the textbook, yep. Okay, so 2 things, and you guys can kind of wiggle between these at your leisure. So on page 79, questions 25 and 26 are 2 just simplistic explain questions about mass spec. It's just kind of a background concept. And then 78 and 79 are 2 mass spec problems that you will be solving from data or from a graph. Okay, and then number 101 is another similar question, which is actually regarding some. That's 110. My bad. Is another similar question, but it's got 3 isotopes there. So just practice the graphical stuff for the moment. So make sure you're fine with 78, 79, and 100. You can start with those. And then we'll bounce back to 20, 20 or 25 and 26 because they're more back on conceptual models, and then we'll go back to the worksheet that's in practice. Okay? I want to make sure that you guys can see data into a problem and then practice. 78, 79. Good question. If you have a more accurate mass given than just the mass number, use the more accurate mass given, which would be like 28.00.
you plug, that's this number. That's 8 here, so it's 29.955. And then you multiply that by 3 and get whatever actual atomic mass.